Regression with PyCindy and genetic programming module in Python called GPLearn. Oh, I should probably zoom in. Oh, it would have been helpful. Do folks want me to put up the station like screens, or are you okay with just the? Is there anyone who's desperate for a station? You want one? Okay, very good. All right. So first, can people make sure there's nothing on their nothing on top of those little tables where the screens come out, because we had that issue last time. All right, they're gonna go up. So everyone protect your laptop. Board students have checked their no items. Okay, well, I've done that. Oh, yours didn't go up? Oh, I'm sorry. I think sometimes they don't go up and then they have to reset the whole system. Yeah, sorry about that. We'll give folks a few more seconds. Okay, so so we're going to cover some simple implementations of symbolic regression using PyCindy and GPLearn, as I said. So just a little spoiler, so I was telling someone about this earlier. The interesting thing with GPLearn is since I put this notebook together, our materials were due a while ago for this academy, since I put this notebook together, it appears that GPLearn is no longer consistent or compatible with the most recent version of scikit-learn. So basically, what that means is we'll walk through it quickly so you get an idea of sort of the components of programming, of genetic programming algorithm, but there are newer implementations. So there's like PySR, so Python Symbolic Regression. I believe there's something else, and I think they're supposed to be much faster, much more powerful. I'm not familiar with them, so I'm not sure how intuitive they are to use, but we'll at least trial with GPLearn. It'll give us some idea of how genetic programming can work in Python. Okay, so I'm not going to go in detail through this introduction to Cindy. It's basically a review of what we talked about earlier, but it's there for your reference if you are so interested. So I'll just sort of skip the front end. So recall that in practice, applying Cindy requires a set of measurement data collected at sort of equally or equidistant time points, so in a particular matrix of size n times n. And then the time derivatives of the aforementioned measurements as well, so you can either measure them directly or approximate them. You get this x dot matrix. And then you need a library matrix theta of x whose columns consist of the chosen set of basis functions applied to the data. So we'll see the construction of all of those below. And as a reminder, our favorite word, sparse, we seek a set of sparse coefficients collected into a matrix of C, such that, this doesn't format very well, but such that we can represent or approximate our function that describes relationships between our variables using our library and then our final coefficients C. Okay. So basically, and then we get the sort of final form of our approximation using each of the terms described above. So how does this translate into PyCindy? So basically, submodules of PyCindy are aligned with each of the terms in the approximation equation. So you have this differentiate method, which performs numerical differentiation to compute x dot from x. If you don't have those already at hand, the derivative is already at hand. You have this feature library module that allows you to specify a set of library functions and handles the formation of the library theta. And then you have this optimizers method, which provides, or option, which provides a set of sparse regression solvers for determining C. So the Cindy object encapsulates one class object from each of these three submodules and uses them along with your data to find a proposed governing dynamical system. So we're going to suppose that we have measurements of the position of a particle obeying the following dynamical system, and it's represented in this form here. And so the system of differential equations decouples into two into two equations whose solutions are provided here, and so these are going to be the, there's a typo here, let me fix that, in real time, hold on. So basic, oh, I have to go down. So it should be y naught times e to the negative t, sorry. Oops, okay, great. So the first thing we're going to do is we're going to install PyCindy, so it's not something that you can just inherently import from Google Colab. If your PyCindy is already installed for some reason, make sure you update it to the latest version, which I believe is 1.75. Let's hope so. So that'll take a second because it's installing. Okay, great. And then we're going to import a number of additional packages that we'll use. So obviously now that we've installed PyCindy, we need to import it. We'll import NumPy and then plot or matplotlib pyplot for plotting. Okay. So our next task is to simulate some data. So just sort of to emphasize, the point of this sort of coding exercise is not to introduce you to problems where you would really want to use symbolic regression. These are very simple problems that you could work through with other less complicated methods. You don't necessarily need something like machine learning to solve these. You don't need Cindy or genetic programming. But the point is to show you how to, the implementation of these modules, not to demonstrate how to use these modules on very complex problems. So if you're like, why is this equation so simple? That's why. Okay, so the first thing we're going to do is we're going to set our initial conditions for x and y. We're going to define a maximum time, a time step, and then some sample time points, which we're going to call tseek. And then we're going to sample our x and y values, or we're going to sort of set up our x and y sequences. So these are sort of samples based on the time that we have the time increments that we've defined above. So let's do that. Great. And so we're going to plot our data. We're going to plot them as a relationship between sort of x and y, not over time, just to sort of visualize their relationship and then the initial condition, where they end up, etc. And we'll use this to sort of compare performance in our final model at the end. So the first thing we're going to need to do for Cindy, beyond just sort of simulating our data or generating some toy data, is we'll actually create x, which contains both big X, which contains both our variables x and y. We'll do this using NumPy stack. And so the first column will be x, and the second is y. And we can sort of visualize the top of that X matrix, so where we have x in the first column, y in the second. Okay, and so the next thing we're going to need beyond having our x is our x dot matrix. So we can do this in a couple of different ways. So one is by hand, and then one is by passing our differentiation method to the Cindy object and let the computation of x be handled automatically. So what we'll do is instead of calculating by hand, we're first going to try selecting a differentiation method from the differentiation submodule. So in this case, what we're doing is we're not calculating x dot at this point. What we're doing is we're just defining our differentiation method from this submodule, from the differentiation submodule. So you can call it two ways. I'm not really sure why. You can use just PyCindy, or we import it as PS above, PS.finite difference, and select an order. So we'll use order 2. You can change that if you want. But you can also call it from the submodule directly. I don't know why they do that, but anyway. So we'll define our differentiation method. Okay. And so you'll recall that we have x, we have x dot. Well, we also need to construct a library. That's a very important part of Cindy. So there's a number of different ways or different libraries that you can build. So in this case, we'll just do a polynomial library of degree 3. We can kind of cheat a little bit. We know that that'll work for the equation that we're trying to capture. But in reality, obviously, you have to use sort of domain knowledge of these assumptions to build your library. So for example, when I was working with Cindy, and you can combine libraries as well. So I would use a polynomial library. I would build a custom library with specific sort of functions that aren't predefined in existing PyCindy libraries. I'm trying to remember what other libraries I use. But anyway, you can combine a bunch of different libraries into your feature library. In this case, we'll just use our polynomial library of degree 3. think I already read that. Anyway, okay. So next we're going to select an optimizer which should be used. In this case, we're not going to use any sort of like L0, L1, L2 regularization. We're just going to use the sequentially threshold of these squares. We're going to set a threshold. So in this case, we're going to set a threshold of 0.2, which you'll recall from earlier means that any coefficients, as we go through this round of least squares and then thresholding, any coefficient whose magnitude is less than 0.2 will be thresholded to 0. And then least squares will be performed again. And so just to emphasize, like we talked about earlier, something like the threshold for sequentially threshold of these squares, or the penalty or regularization weight lambda, if you do something like ridge regression, those are hyperparameters in this case. So it's something that you are going to want to explore different values, hopefully in some kind of systematic way, and then select parameters, or these hyperparameters, based on some sort of performance metric. Okay, and so finally, we can combine all of these pieces into one Cindy object. So basically, we're going to define our model, and we're going to give this Cindy method a bunch of different options that we've defined above. So there's the differentiation method, which we defined above, that finite difference, our feature library, which we defined above, our optimizer, and in this case, we're going to provide feature names so that when we print the equation, it's more interpretable. If you don't provide that, I'm trying to remember if it does like x0, x1, x2, or something like that. Yeah, so it's nice to actually provide the feature names for interpretability. Okay, so we first instantiate the model object, and then we'll fit the model afterwards in a single step. So this should look familiar. It follows scikit-learn, it follows TensorFlow workflow. So we've instantiated above, and now we're going to fit. And so the way we fit is we provide this X matrix that we have, which is sort of the stack version of our X and Y vectors, and then our sequence. And this will correspond to sort of the times the time sets that are represented in our big X matrix. Okay, don't panic. Unlike the last time that I gave a coding tutorial, I actually anticipated this error.
I will tell you the solution. Make the web install numpy equal 1.26.4 and scikit-learn equal 1.5.2.
Sorry, say that. What are you saying?
So we will go to the first of them. First, go up.
Yeah.
Go up. Up again. Yeah. So decomment the mySyndy.
Wait, sorry.
mySyndy, make comment for it. Comment it.
Oh, yeah.
Okay, and write web install. No, make comment. Comment this and comment the hour.
Sorry, I'm not hearing you.
Comment those. Okay, I will show you.
Yeah, thank you.
So just comment those and run this one.
Oh, okay.
Okay.
All right. So what we'll do? So if you wanna, yeah. So maybe what I'll do is I'll fix that in the final notebook. There's an easy way to like move on from the error that we have.
Yeah. Okay.
Yeah. Yeah. No, that's great. That's great. Thank you. Okay. Okay. So basically, yeah, the outcome from that is that apparently there's a way to fix the error that I was not able to find. So that's great news. It's not going to be fixed in this section, but there's an easy workaround. So what we're going to do is we're going to continue with what's in here, but then I'll update the notebook afterwards so that you have the correct implementation. Okay, so I guess one reason to sort of keep the error in is that, or at least the reason that I originally had an exercise on this where you're going to find the source code, you're going to import it, blah, blah, blah. I don't think that maybe that's the most fun exercise. But this is at least a nice example of you can get an error and then in Google Colab you can go to working hard. I don't remember it taking this long before. But ideally, oh yeah, here we go. Okay, and it'll explain to you sort of what's going on. Here we go. In this notebook, this is a known issue in this version of PySyndy. Since we've already addressed this by importing updated finite different class from our file, we can proceed with the rest of the notebook. So, great. It knows that I've imported an updated finite difference class, and that's what we're going to do to solve this. So basically, in the original, at least when I originally was working with this notebook, there was an issue in the current version of PySyndy that was available via Pip. So if you went on GitHub, it had the correct code, which was great. So clearly they had fixed it, but for some reason that had not made its way over to Pip. So what we're going to do, if you wish to inspect the source code for finite difference in the current version that's installed, you can run this import inspect and then this code here. And basically what it'll show is that there's an issue under the coefficients boundary forward method. It has to do with it calling something from math that, that our NumPy has no attribute math. Okay, so instead what we're going to do is we're going to do a little less elegant way than what was suggested as the solution before. We'll import the updated source code, taken from GitHub. So we'll overwrite the previously imported class definition using this new class definition. And so in order to do that, we'll need to import base from the PySyndy GitHub. And we'll use wget for this, which is probably a command most folks are familiar with. We'll get the updated finite difference class from a Google Drive folder that I've made. So that's provided here. You'll need gdown. You would have seen this in the coding exercise that I did last week. And then we'll make sure to set our working directory to the directory containing our required file and import the class. So the file is called finite difference underscore updated, but the functioning is the same as the one we want to overwrite, obviously. So you can run that, or you can just watch me do it. It's going to give us a little bit of a verbose input. Okay, great. So the reason that, I should say that another reason that I couldn't import the finite difference class directly using wget is because it had, it imported dot base as opposed to just base, so the definition would not have worked. Anyway, okay. So now we're going to use the corrected finite difference class to find the bug. So we're going to redefine our differentiation method using our new class. We're going to call it model retry, and we're going to provide the same differentiation method, the same feature library, the same optimizer, the same feature names, etc. And now we're going to try to fit, we're going to fit our model retry using the same x and t set of sequences. Okay, no one panic. I was aware there was going to be another error. So basically, this may actually be fixed in the solution that was given before, and when I update the notebook. But there appears to be an issue with the differentiation method, that finite differences method, in computing the x dot. Something with the dimensions, so I checked the dimensions of x, the feature library, the feature names, etc. It was unclear where the matrix dimensions error is coming from. So what we're going to do is demonstrate how you actually don't have to use the finite difference method from PySyndy, and you can manually calculate x dot. So to do that, easy peasy, all we have to do is from NumPy use dot gradient, give it x, and tell it the t-step, or sort of the number, our time steps corresponding to x, and then it will compute x dot. Great. Okay, and so in this case, we have our model retry, and we provided a differentiation method, but we can sort of bypass that by providing, in addition to x, our set of time steps, we can provide x dot, which we defined above. Okay, great. So there's success relatively in this case, in that we were at least able to fit a model and not get an error this time. So let's inspect the governing equations, and we can do that by just doing our model name and then dot print. Okay, great. Hopefully, if you run these things, you've recovered our expected equations. What we're going to do now is we're going to try to spice things up, maybe break things a bit more, and try a new set of equations. So I had the painful experience of finding this out on my own. But basically, if you redefine your library or your optimizer, the the pieces given to a previously defined and fit model will change within that previous model. So if you want to reuse a previously trained model, the model will have changed, the learned equations will be different. Because of this, we need to always define a new library and optimizer for each model just to be safe. So basically, if you define differentiation method, or let's say you define your library to be a polynomial library of degree 3, and then you fit that model, retry, you get an output. If you define your library with the same name after you fit that library, or after you fit that model, and you use a different library, like polynomial degree 2 or something like that, it will affect the model you've already trained. That's a bit verbose and maybe not easy to follow, but the core point here, for if you're going to be playing around with this code on your own, is that it's always best to give, when you create an optimizer and a library for a new model, always give it a new name, so that you don't overwrite models you previously, or change models you previously fit. Okay. So basically, all we're going to do to generate new data is change from e to the negative t to just e to the t. So that's a pretty simple change. We're going to use our same time sequence. We don't need to worry about changing that. We're going to use our same initial conditions. We're going to create a new x. We're going to call it x new, because again, we're trying to sort of make sure that we keep all of our pieces for the different models. We're trying to create separate pieces for each model. We're going to stack those together. We're going to use this empty dot gradient to avoid all those errors we got before to create our new x dot. We're going to create a new optimizer. It's the same as the one we used before, but just for safety purposes, we're just going to redefine it. We're going to instantiate the new model, so we're going to provide it our differentiation method, which we technically I don't think we need to provide because we're providing x dot, but anyway. Our feature library, which we're not changing. Our optimizer, and we're just going to give it a new optimizer just in case. I guess if I was really thorough, I would create a feature library. Wow, okay, I love that automatic coding, right? Okay. Great, okay. And then we're going to fit the model, passing the time sequence t, as well as our new x and our new x dot, and we're going to print that new model. Okay. So this is our resulting equation. Hopefully you got something similar and I haven't messed with the code too much. The second equation looks pretty good. We were expecting just y. But our first equation looks pretty complicated, or at least more complicated than minus x2 or 2x. So one thing to note is that our x and y values are in different orders of magnitude. So this was sort of a question that was asked earlier. And differences in magnitude between variables can definitely cause issues like this in symbolic regression. Basically, in our case, x is much smaller than y, right? We have a negative exponential and a positive exponential. And so the symbolic regression is likely overfitting x with overly complex expressions while recovering y more cleanly. There's a little bit more explanation about that below. So what we're going to do is we're going to rescale our input values to the roughly the same order of magnitude and try again. And just note, if you do this to get your equation back in the original units, you need the inverse transform, etc. Okay, so we've seen standard scalar before, I'm sure, for scaling data. We're going to we're going to instantiate our standard scalar, and then we're going to fit and transform our x new into a scale version, and then our x dot new into a scale version as well. And then we're going to fit, and we're going to print. So it's pretty standard. Okay, so now both of our expressions are relatively complex and not what we were hoping to recover. So this could be an issue due to another sort of limitation of Cindy, which is that you tend to need a lot of data to work with Cindy. So this could be due to only having 121 time steps with a relatively large feature space. So for example, library 10 terms. So with this, the system can be underdetermined, which basically just means we don't have enough information to uniquely determine values of all unknowns. And so there's a few possible fixes. One is to reduce the feature space, so lower polynomial degree, dropping interactions. You can increase sparsity, so a higher threshold for sequentially threshold of these squares. You could use a regularized optimizer. For example, you could use something like ridge with an alpha value. Provide an alpha value, or you could add So we're going to try, we could try all these options, but for exercise 1, it's going to give you a simple pass at sort of redefining the components of the Cindy model and fitting that model, and we're going to see if it's enough. So this is going to be exercise 1. The code should be provided below, but you can take a few minutes to do it on your own. So basically I've provided, if you're so interested, I've provided a few steps here. So basically make smaller polynomial library, instantiate a new optimizer, instantiate the model, and then fit and print the model passing the time sequence t. So yeah, so that should be about it. And you can use, I'm trying to recall, don't look so fast while we go. Which one do we use here? Okay, and so instead of using the scale, I just give it our x new and our x dot new from above. Okay, so you can work with that data. Okay, so we'll take, I don't know, I'd probably be pretty quick for you folks. You've seen a lot of Python, and this is relatively simple compared to things that like John was doing, for example. So we'll just do 5 minutes. Any surprise? So basically, as I have put above, I put some steps. So 1, make a smaller feature library. As I mentioned before, you don't want to just call it feature library, because that's kind of basically, if we had our model retry that you recall we had above with our original data, that will change the feature library that's underlying that model. So we want to give it a different name. We're going to instantiate a new optimizer. And again, we're just going to call it degree 2 because it pairs with our newer, smaller library model. We're not changing the optimizer that we've used, so it's probably not necessary, but out of an abundance of caution and all of the issues I was having when I was trying to figure out why models were changing, I redefined it. And then I'm going to instantiate the new model. We're going to call it model sparse, just in this case because we're using degree 2 instead of degree 3. We're going to provide our different options here. Again, probably don't need to provide a differentiation method, but apparently I kept feeling like doing that. We're going to make sure that we're providing it our degree 2 feature library and optimizers. And now we're going to fit our model again. Okay, it still doesn't work, but we appear to be getting closer in the sense that at least we're getting a sparser model. But another thing that we sort of mentioned is that we could add more time points if possible. So this is a very nice thing to try when you are just sort of simulating data. In the real world, it's probably not very practical or possible to just go out and easily simulate capture or measure a bunch more data. But let's see how it works for us. So basically, what we're going to do is we're going to increase. Well, I should say sampling frequency. Oh, did I? I did actually. I think before was a different value. Anyway, okay. So we're going to increase. We're going to sample at greater frequency. So a little counterintuitively, I call this t-step long, even though it's a shorter step. But anyway. And so we're going to create our new sequence, and I guess long here just refers to the fact that we have a longer set of sample points. Okay, and so we're going to sample new x and y values using our same sort of updated set of expressions. Again, using our new sequence. We're going to create a new x matrix. We're going to create a new x dot. Again, using all of our sort of underscore long objects. We're going to make a smaller polynomial library, or you can reuse from the above exercise. And we're going to make a new optimizer, and just to be safe. Okay, and so now we're going to instantiate the model, and we're going to fit the model passing the time sequence t seq long, which I should have there's a typo there in the comment, because obviously now if we provided passing the time step. So if we just use the original t-step, it wouldn't match what's going on with our x. Okay, and we've had success. So again, we recover basically our minus 2x and then just our y. So this highlights sort of two limitations of Cindy. So one, Cindy results are highly sensitive to the construction of a library, which requires user input. So it's basically, you can say it's not agnostic, or it's not completely, what's the word I'm looking for, objective, I suppose. So this can help incorporate domain knowledge, so you can sort of limit the number of terms, certain terms are going to be really important. but it can make the results subjective to the user, especially in cases where you really have no idea what terms you should be including. And also, Cindy can be quite data hungry, so even with 121 time points in a smaller library, we struggled to obtain our equations, and we had to increase sampling. Okay, so the other thing to note here is that we added no noise to our toy data. So they're basically perfectly, the equations perfectly sort of produce these outputs. And so what happens if we add some noise, which is likely when working with experimental data. So I've sort of defined these arbitrary noise values here, X noise and Y noise. I've created new sequences, and now the longer length, using that TC long. I've created a new X called X underscore noise, a new X dot, redefined our feature library, just for the sake of, I don't know, apparently I'm being very cautious here. And instantiate the model again, now called model noise, and now will fit. So you can see this is a very straightforward and unfortunately repetitive process. Okay. Oh, this actually did well. I'm not sure why it did well. Anyway, basically maybe if I had changed the noise, or maybe actually probably what I originally had was using the shorter sequence. Anyway, time steps. But essentially another issue with Cindy, and honestly an issue with equation discoveries more generally, is that their success can be limited by noise. So one thing that we can do is we can change the sequentially threshold of these squares threshold to see if we recover our sparse equations. I'm a little concerned because we actually got our equations, so that's not going to be a very helpful exercise. So let's see if we use less data. Okay, great. Okay, so just if you have in the code where everything is according to the longer set of, or the increased frequency sampling, then just go ahead. I apologize, I'll modify that. So it just uses the original time sequence. So that showed up under xseq and yseq. It would have showed up under x dot, and it would have shown up under the fitting for the model. Okay. So as I said before, there can be issues with noise when you work with Cindy. And so let's see if we can change our threshold to recover our sparse equations. So this is going to be your second exercise. Again, pretty straightforward. You're going to want to think about what direction should we change our threshold to obtain a sparser equation. And so for exercise 2, you're going to choose a new threshold to see if you can recover the expected sparse equations. And then you get bonus points for creating, well, I don't really have anything to offer for your bonus points, but you can try creating just a simple looping structure that tests multiple thresholds and prints the resulting equations. So again, make sure you define a new optimizer because you don't want to say, you don't want to use optimizer noise and then redefine it because then our original model noise is going to change. Okay, so I don't know, take about, we'll say 5 minutes again, and then you also have the option of sort of trying different thresholds in some kind of looping structure if you were so keen. So what I did was I defined a threshold list because right with a for loop, a list is something that is iterable. So I defined a list and basically just tried different orders of magnitude. You could try the same order of magnitude with different values like 0.1, 0.2, whatever. And then we can iterate over that threshold list if you were so interested in doing the looping structure. And so basically, I called the model model threshold. I don't need to save the model necessarily, so it's okay that I'm rewriting it every time. You could write it there. You could create a new model for each value if you wanted. And we're going to use our same feature library. And then, right, so in this case, you could actually define a new optimizer. Or you could just sort of provide the optimizer directly by passing in the threshold. And then we'll fit our model, and this is the version with noise, right? Oh, and again, we changed to just, what should be X dot noise, I think. Okay, very good. All right, so let's take a look. Ooh. the point here is that you can loop over different thresholds, and then you can see how this will have consequences for the actual equations that you obtain. Unsurprisingly, that the higher your threshold, the sparser your equation will be, right? Because you say any coefficient that falls below that threshold is going to be zeroed out. And so in reality, this is a pretty simple way to try different thresholds. What you would want to do in reality is that you would want to do some type of hyperparameter tuning, say via cross-validation, to actually try to select an optimal threshold. And the same thing you would, if you were to do incorporate some kind of sequentially threshold of least squares threshold with some sparsity weight like alpha for ridge regression, then those are two hyperparameters you would want to sort of more systematically tune based on something like cross-validation. Okay. So basically, looks like when we add noise, you can sort of obviously obtain sparser equations by increasing the threshold. This would be true even if we didn't add noise. It's sort of good news in part, because that's what we would expect. But in practice, we won't know the correct equation, so it'll be hard to know what hyperparameters like the threshold to actually choose. So after generating our predictions below plotting them, we're going to leave Python and we're going to move on to genetic programming. But as I mentioned, you can imagine how you would use something like cross-validation. So in order to generate predictions, you can use this Symbolic method that is attached to your model class. So we're going to give it a desired prediction window that we want to simulate over. You could use the same sequence that we defined above, and then you're going to give it your initial values. Great, and now we're going to replot sort of what we did earlier, but we're going to overlay the initial, we're going to overlay the real values to what we get from our simulated data. And so the way we're going to do that is we're just going to sort of call the first column from our simulated data and our second column from our simulated data. And yay! Okay, because we obviously above, when we actually did the model retry, which is somewhere up here. Here we go. We basically perfectly obtained our set of equations that generated the data, so it's not exactly shocking that we got a perfect fit, but obviously we had differences between our sort of true dynamics and our larger differences between our true equations and our sort of estimated equations. You would get such a perfect relationship. Okay, so this is just a brief introduction to PyCindy. So what we've done in this section is installed and imported PyCindy. Again, I'll go back and make sure that we have the correct sort of compatible versions installed and imported so that we can get rid of that error. But we did debug some issues with PyCindy code, which is always a nice thing to practice doing. We successfully fit a simple PyCindy model. We tried a new simple model, which initially failed to recreate our expected equations, and we implemented a number of changes to our model to, well, we didn't successfully obtain our expected equations, but I imagine if we had used sort of the less frequently sampled time series, we would have been able to do that. Okay, so beyond the simple intro above, there's some extensions, so custom library construction, so I alluded to this before, you can define your own, I don't know what that means, define, your own, there we go. Oh my gosh, there we go. Okay, you can define your own candidate functions beyond, say, polynomials. You can do hybrid libraries, so combine multiple libraries. You can choose different differentiation methods, which can be helpful for noisy data sets. You can do model selection and cross-validation using a method called model score. You can use control inputs like SymDC by basically providing this U value, which is like X, but for your control variable, and then provide it we want to predict. You can use ensemble methods, so we'll cover that tomorrow, for example, or sorry, Friday. An ensemble method like bagging. And then you can also create custom optimizers by creating a class. And so these are all possible in extensions to PyCindy. So again, this was pretty simple, but it gives you a little bit of a flavor for how Python works. Okay, and so next we'll do a quick overview, or a simple overview of Introduction to Genetic Programming using GPLearn. Just to get folks excited, I think we'll probably be done at least by 4, so woo-hoo! Okay, so basically, GPLearn implements genetic programming in Python, again with a scikit-learn inspired compatible API. So it can be used for a variety of tasks, but GPLearn, or genetic programming, can be used for a number of different tasks, but GPLearn is purposely constrained to solving symbolic regression problems. So we've already talked about what symbolic regression is, so I don't think we need to overview that, but there's a little bit there in case you're interested. So GPLearn retains, like I said, the familiar scikit-learn fit and predict API. It works, quote unquote, with existing scikit-learn pipelining research models. So a little caveat there, we're going to be able to get it to work with symbolic regressor. And now it's not compatible with the latest version of scikit-learn for symbolic classifier. So basically, I think that GPLearn gives a nice introduction to thinking about how you might fit or set up and fit a genetic program or genetic programming model to estimate or to obtain equations, do symbolic regression or symbolic classification. I think that there's now cases that are actively, or modules that are actively maintained and are more powerful and more efficient, and they're a little bit more elegant. So don't take this to be sort of the ultimate module that you could use for genetic programming. Okay. Right, so in the original implementation, so GPLearn supports regression through symbolic regressor, binary classification through symbolic classifier, and then as well as a transformation for automated feature engineering with something called symbolic transformer. Okay, so we'll get started. So first we'll need to install and import the GPLearn module. This works. Okay, and so like we did last time, we're going to generate some toy data that we're going to work with. So in this case, we're again just doing a range of values for x0 and x1, and then we're going to combine them using this np.meshgrid, and then we're going to calculate sort of our true y, or our target value, by combining these x0s and x1s in a particular equation form. And just as a reminder, this double asterisk in Python performs exponentiation, so we're squaring this x1. Okay, and then we'll plot, we'll make a rather fancy looking plot, a surface plot to show the relationship between x0 or x0, x1, and then our true y values. Very fancy. Okay, so right, so that's generating our toy data, and so what we're going to do is we'll create some random training and testing data from this. So we're going to, in this case, we're going to do it a little bit differently than using train test split from sklearn. So we're going to sort of use this uniform and reshape here, and so basically it's going to randomly select. It's going to randomly provide these x values of a certain size, and then we're going to again use our defined formula above to calculate our y. So we'll do this for both training and testing. Okay, so now we're going to consider how to fit symbolic regressor to this data. It's a fairly small data set, so we can use a pretty large population to explore it, since training time will be pretty fast. Okay, and examining the equation, it looks like the default function set of addition, subtraction, multiplication, and division will cover us. Obviously, if you think that you're going to have a more complex equation, you're going to need to sort of modify the function set that you provide to GPLearn. Okay, and so there's a few things that it'll provide. So we're going to watch this OOB error evolve. So it's basically calculated by averaging the prediction error on each training sample sample using only the equations where that sample was not used in training. So it provides this unbiased estimate of the model's performance without needing a separate validations set. Okay, so if you want to know all the arguments, you can go to the documentation for symbolic regressor. I linked that there. You can also, I think they could be some of them are pretty intuitive if you actually look at the code down there for what the arguments are. And then it will print out some things as it's training. So generation, the current generation of the evolutionary process, the length of the number of nodes in the best program of the current generation. So it's a measure of complexity. Each node represents a function or a terminal. And then a fitness score. So it's often mean squared error or squared depending on how it's configured of the best program in the current generation. So this is how we would set it up. You would use symbolic regressor, specify population size, number of generations if you have a stopping criteria, the probability of crossover, probability of subtree mutation. I'm not sure what voice mutation is. Buried in there. I'm not sure. We'll have to go back. Anyway, okay. And then we're going to do things like we're going to set verbose to 1 because we want to watch it printed. We're going to provide some parsimony coefficient, provide some random state for reproducibility, and then we'll provide our x train and our xy, which we defined above, for fitting. So this should look pretty familiar. You instantiate the model and then you fit it. Looks a lot like scikit-learn, looks a lot like TensorFlow, etc. Okay, so we're going to watch it output some things. So obviously here's a generation or length. So that kind of describes how complex the equation is. Fitness, and this is talking about population average, and then the best individual. And this is time. So I'm trying to think if we specify what that time is. But anyway. Okay. So it's gonna keep going here. I promise I'll only take another second. Okay. And so when this sort of blue box pops out, that means that it's trained the model. And it's providing that model in a rather weird form here. So you may have noticed that we said the maximum number of generations is 20. It went to, I guess, 7 by Python indexing. Right, because the error was better than the threshold that we provided, that stopping criteria. Okay, it also appears that the parsimony coefficient was made just right as the average length of the program, so that's sort of given y for the individual as well for the population. Seemed to fluctuate around a little bit, but then it stabilized. So let's take a look at our solution, which we kind of already printed out about, but we'll do it anyway. So it doesn't have the same structure as our target function, and it probably looks a little unfamiliar or in a slightly strange form for most of the folks here. But you can rearrange it to get into a form that is maybe a little bit more familiar looking. So we just expanded out, we combined like terms, etc. There are terms that cancel. We're left with almost the exact relationship we expected. So this is 0.909 as opposed to 1. So this shows for obviously a pretty simple problem. It was able to do it pretty quickly, and we got back our ground truth equation. We can compare with other nonlinear models to see how they do. So one, we could instantiate this decision tree regressor. We could also try a random forest regressor. So we'll give it the same training data and see how they do. Fortunately, those fit very quickly. And then this is basically a bunch of code to just plot the decision surface and visualize each model, compare them to each other. So we're going to do the ground truth. We're going to plot that. We're going to plot the symbolic regressor output, we're going to plot the decision tree regressor, and we're going to plot the random forest regressor. Okay, so let's do that. Okay, so this is what it outputs. So you can see what the surface looks like for the relationship between x0 and x1 and y. And it's giving the r squared on the testing data above. So a few things we can notice. We were able to fit a very smooth function to the data, while tree-based estimators tend to create blockier decision surfaces. The random forest appears to smooth out some of the wrinkles, but in most cases, the models have fit very well to the data, but they've done worse on out-of-sample data, so given by the R-squared there. So we can also inspect the program that the symbolic regressor found. Okay, and so when I say inspect, so basically we're going to be looking at this tree representation. And so this is, we sort of saw these different types of expression trees before, and so you can work through this and sort of see how everything, when you combine everything in the tree, we get back to either sort of that strange representation of the equation or sort of the more familiar expression. Okay, so that was pretty straightforward, I think. It comes from the GP Learn documentation website. The last thing we're going to do, and I think this will be pretty quick because I've pickled everything, you should be able to just load in the model, is try some cross-validation for hyperparameters. So we'll use CV grid search, which I introduced in the model evaluation session last week. So basically, we're going to reinstantiate our base symbolic regressor. Again, we're going to specify things like our population size, number of generations, etc. This time, we don't need to spit out everything at us. The trace basically is just going along and fitting, so we're going to say for most equals 0. So we'll do that. Okay, and so now we're going to perform, I'm going to give you sort of a couple options here since we have extra time. So one thing I wanted to do was provide the fitted model so you could just load it in from this pickle file, which basically, if you weren't here last week and have no idea what I mean by a pickle file, it's just sort of a Python-specific way to save, say, a model object. You can save other things with it, but in this case, a trained model, and then reload it back in at a later date. This allows you, if your model takes, a zillion years to train, well, you don't want to have to, every time you need to work with it, you don't want to have to retrain it. And it also makes your model accessible to other people if they want to load it in and work with it. Okay, so what we're going to do is, so we should have already set our working directory, hopefully we did, we set our working directory to the Google Drive that contains this pickle file. So just to sort of walk you through what's going on here, we set our path. So we're already in the working directory that holds it, so we just need to provide the name. We can check if the model is already saved. So basically what this is going to do is say, we're going to call our grid search model, grid_search, and so if it's there, we're going to pickle load from that using our model path, and that'll load in grid search. If it's not available, we need to do it ourselves. Here's how we would do it. So we would define our estimator. So in this case, we're redefining it. So our estimator is just this symbolic regressor. And then, so I guess we did instantiate up here, but if you do this, you're just reinstantiating it down here. And then you can grid search over symbolic regression hyperparameters. So we're going to set up a parameter grid. In this case, when I ran it on Google Colab, it took about 12 minutes, even with just sort of 2 hyperparameters, each with 2 options. On Jupyter Notebook on my own machine, it was much faster, so if you run it on your own machine, you may be able to get away rather quickly with trialing more hyperparameters. And then for grid search, you would use grid search CV, you could do random search CV, whatever options you want. Provide your instantiated model, your parameter grid, how many sort of polls you want to do, what score you want to do, the number of jobs. I believe that if this n jobs -1, I believe that would be sort of what's available -1, but I would have to double check. Right. And so, and the other thing, so when we instantiate this symbolic regressor, there's other arguments that we would need to pass, that we could pass, so we specify a bunch of options up here. So what we kind of settle with here is the defaults. And then you would do, like you would do with any other model, you would do grid search.fit, and you provide your training. And then it would save the trained model when it's done using pickle ... using the model path that you specified above. And then when it's done, it will helpfully print out the best parameters and the best cross-validation score. So because this file already exists, it'll just load it in for me. If you want to on your own time, you can of course, if you're interested in trying a more complex model, changing the the arguments to symbolic regressor, providing more hyperparameter options for your parameter grid, you can certainly modify the code to do that. Okay, and so from after loading the model, it gives us the best, what it believes to be the best parsimony coefficient, population size, and the best cross validation score. Okay, so now we can get our best model, which is in hyperparameters. And you're gonna, you can do that by just extracting the best estimator. So basically, the best model is stored in grid search. We can just take it out, and we'll print our final equation. Okay, so in a more interpretable form, this is what our final equation looks like. Obviously, it looks a little silly in this first form. Why would you have x0 or x0 over x0? I'm not sure, but that's where it arrived to. You can factor out combined like terms and rearrange. This is pretty nice, given that our original expression is identical. Okay, so I believe this is about the last thing we're going to do. We're going to give our testing data to our fit model, predict, and plot. And not surprisingly, because we perfectly reconstructed our equation that we used to generate the data, we get this perfect sort of one-to-one line between our true y and our predicted y. So isn't that nice? Okay, so it looks pretty good. We've covered regression here, but if you, right, so I was saying that you could technically try to play around with symbolic classifier, and I usually have an example in here where we use iris for that. With two species for binary classification, but there seems to be some issues with GPLearn not being updated, so that's a little sad. But anyway, in this session, we've installed and imported GPLearn, we trialed symbolic regressor on toy data and compared to other models. We've covered an example of cross-validation for hyperparameters. So, as I was saying before, beyond simple GPLearn intro, you could try and give it a crack with symbolic classifier. I imagine that it would again require some kind of specific importing of scikit-learn rather than the latest version. But I would really encourage you to explore PySR, which is supposed to be quite fast and uses a Julia backend with a Python interface. So that's what I would recommend trying for your own projects. I haven't had a chance to explore it yet, but it's certainly where I will go.